we go with our last lesson check of the year. We are looking at 7.4. So we are going to start with number 49. When a collision occurs, how are the initial and final momentums of the system related? This is going to relate actually back to the last section of the chapter. We are looking at the fact that momentum is conserved. So for number 49, we're looking at momentum is conserved. So the total initial momentum is equal to the total final momentum. So the individual momentums in the system will not necessarily be the same before and after the collision, but the total momentums of the system will be. So that's sort of the big idea that we're talking about with number 49. For number 50, we're looking at how is the initial kinetic energy related to the final kinetic energy in an elastic collision. That is the important word here. In an elastic collision, not only is momentum conserved, but kinetic energy is conserved as well. Right? That means our total kinetic energy we started with is equal to the total kinetic energy we end with. We are looking at the fact that it is the kinetic energy of each individual piece added up before the collision, and the individual pieces added up after the collision. So that is going to be true for an elastic collision. In an inelastic collision, we're not going to have the same initial and final kinetic energies. Some of that energy is going to be lost, is going to be transformed into a different form, right? The kinetic energy is going to be transformed into heat or sound. Or into permanently deforming an object. Right. So a permanent deformation, a permanent change in shape is going to result in a loss of some of that kinetic energy. Number 52. What do we call a collision in which the colliding objects stick together? If we have the colliding objects stick together, it is going to be called a completely inelastic collision. All right, so completely inelastic collision, objects stick together. Just a regular inelastic collision, the objects are not going to stick together, but we are going to see a loss in kinetic energy. All right, number 55. A cart of mass m equals 0.12 kilograms moves with a speed v equals 0.45 meters per second on a frictionless air track and collides with an identical cart that is stationary. The carts stick together after the collision. They stick together after the collision, so we are looking at the fact that number 55 is a completely inelastic collision. Sorry, my handwriting got a little crazy there. But we are looking at the fact that it's completely inelastic. So we looked at some of the problem solving in the lecture where completely inelastic we saw that it was m1 v1 plus m2 v2 is equal to m1 plus m2 vf. Right, so the individual momentums before the collision is equal to the final momentum of the now new combined super object. So let's take a look at what that looks like. In this particular case, they are identical carts. So M1 equals M2, which is that M of 0.12 kilograms. V1 was that V, which was 0.45 meters per second. V2, stationary. So that's at rest. Right? So we went ahead and sort of gotten a couple pieces of information. So let's rewrite this to sort of simplify out. So we're looking at the fact that M1 and M2 are both M. V2 is 0. So this term actually goes away. So I'm going to have M times V, since that's what this is, plus 0 is equal to M1 plus M2 are both M. So 2M times VF. All right? So that goes ahead and simplifies some stuff for us. Now we can go ahead and solve for VF. When we do that, I get VF is equal to M times V divided by 2M. Notice those M's are the same in this particular case, so they cancel. So my VF is going to equal 1/2 of my initial velocity. All right, and we do get a final velocity of 0.225 meters per second. We do only get 2 sig figs, so we do need to go ahead and make some adjustments to that. So it's going to be 0.23 meters per second. Right. You could have gone ahead and left that math in there and done all the math, and you're going to get the same answer. But there is a reason why I like to sort of simplify things out, because I was able to do a lot less calculations, a lot fewer calculations because of this simplification I did here. All right, so our last question, number 58. All right, Brittany stands at rest on a skateboard. The combined mass of Brittany and the skateboard is 61 kilograms. I'm going to call Brittany and the skateboard M1. Dave tosses a 3.7 kilogram pumpkin to Brittany. That's going to be M2. All right. We also noticed the fact that Brittany was at rest initially, so this is going to be V1 is going to equal 0. And when she catches it, she and the skateboard begin to roll backward with a speed of 0.16 meters per second. So she catches it. That means the M1 and M2 become combined. Brittany and the skateboard and the pumpkin are all now one super object. So we are looking at the fact that this is completely inelastic. All right. As a result, we are looking at the same equation we just saw before. All right. This one here is going to be what we're basing this off of. So we're looking at M1V1 is equal, sorry, not equal, plus M2V2 So because this is a completely inelastic equation, we're able to pull that M1V1 plus M2V2 is equal to M1 plus M2 times VF. We were told what the speed that they move backwards with together. So that's that VF is equal to 0.16 meters per second, and we want V2. Because she was initially at rest, this term is 0, and we're solving for V2. As a result, V2 is equal to M1 plus M2 VF divided by M2. We can go ahead and plug and chug at this point. right, so we have the 61 plus 3.7 times 0.16, and all of that is divided by 3.7. Oops. And we do get a initial velocity for the pumpkin of 2.80 meters per second. All right. We have now finished all of the lesson checks for Chapter 7. Please make sure that you get your corrections turned in on eLocker. Have a wonderful day.